Here we will do an example for forward kinematics of an RPP cylindrical robot using the product of exponentials method. The procedure here, step 1 is to assign coordinate frames and omega and joint directions. Then step 2 is to place the P's, initial points of the joints. Step 3 is to find the home configuration. Step 4 is to find the twist coordinates and the twists. And then finally put them all together in the product of exponentials formula to find the base to tip transformation. So for step 1, assign coordinate frames. We need coordinate frames for the base and the tip. Well, we can see the base rotates here with the z-axis going up. So this is z0, and then the tip, its z-axis points this way. And then we want, for ease of rotation figuring out, we want the x directions to point in the same for both. So that would be x out of the page. So x0 and x3. And then the y vectors, this will be y0, and then pointing down, we have y3. So next, the omegas. Well, for the revolute joint, that is just the same as the z-axis vector. So omega initial. Then also for use, let's see, omega 1, since this is the first joint, we'll just say there. And then here, omega 2 will point in the same direction that joint 2 moves. So even though it's 0, its direction is still in the z direction, omega 2. And then omega 3, similarly, still points in the z direction, even though its value will ultimately be 0. So if we write down what each of those are, omega 1 equals 0 in the x, 0 in the y, 1 in the z. These are all given in the world frame, the base frame. And omega is a unit vector because it's just a direction, so 0, 0, 1. Now omega 2 and omega 3 are just 0 because those joints are prismatic, they're not actually rotating. So omega 2, omega 3 equals 0, 0, 0. Then d and theta, well, we can see here, joint 1 rotates this way. So that is going to be theta 1. And then d2 goes this way. And d3 goes this way. Next, we have to place the P's, initial points. The easiest place to do those is on the origin of each coordinate frame or each joint. So let's say for the end effector, we want P to be here. So that is P3. And then here we can have P2. Here we can have P1. P can be anywhere along the z-axis or the omega vector for that joint. The easiest place to put it is at the intersection of the coordinate frame. So P is also given in the initial configuration. So that means that both of these D values are going to be 0. The robot will be all shrunk up on itself. So just kind of what that would look like if the robot is all shrunk in on itself. We'll have revolute joint down here, and then L1 there was given, so L1, but then we've got this little box for joint 2, but D2 is 0, and then joint 3 is also, D3 is 0, so the whole robot is all scrunched up at this spot. So all the initial points are actually just going to be in the same spot. So we've got, this is P, all the initial points scrunched in on each other. Then P1 equals P2 equals P3 initially, which is 0 in the X, 0 in the Y, L1 in the Z, because again, this is given in the base frame. Now step 3 is find the home configuration, T in 0. So looking at this, we can see that to get from 3 to 0, we need T3 0 initially. That's going to be R3 0 initial, and then O3 0, which is the same as P. 0 0 0 1. Now for the rotation matrix, we need to see what is the direction that this coordinate frame faces at the end relative to the one at the beginning. Well, it looks like the X directions point in the same direction, but Y and Z don't. Y and Z are rotated 90 degrees. It's 90 degrees clockwise, so that is negative. So negative 90-degree rotation around the X axis. So R3 0 initially is a rotation around the X axis that is negative 90 degrees. Well, we know how to do that. We have 1 in the X spot, 0, 0, 0, 0, and then we'll have cosine, sine, minus sine, cosine. Well, cosine of negative 90 is just 0. So we've got a 0 here, a 0 here. And then sine of negative 90 is negative 1. The opposite of that is 1. So here we've got the rotation part. Then we can fill out 0, 0, 0, 1 in the bottom. And then finally, we need the origin of that, which is just the same as P3. 0, 0, L1. So this is the home configuration initially. Now step 4, we need to find the twist coordinates and the twist vector. One formula for revolute joints and another formula for prismatic joints. The first joint is revolute. So this is the formula for the twist and the twist coordinates. So we'll have negative omega cross P for joint 1. So if we do that, we'll have negative I, J, K. Omega is 0, 0, 1. And then P1 is 0, 0, L1. Well, this cross product just comes out to be 0 because when you have K cross K, you end up with 0. So that is 0, 0, 0. And then just has omega in the bottom. So that will be 0, 0, 1. So if we write squiggle 1 equals In the top, we'll just have 0, 0, 0. And then the bottom, we have the omega vector, which is 0, 0, 1. So this is squiggle 1. Now for squiggle hat 1, this is going to be a 4 by 4. So we actually have to hat the omega vector. And then we'll be able to put that in for the rotation part. And then zeros on the bottom. And then finally the negative omega cross p for the translation. Well, this negative omega cross p, we already found it here, it was 0. So we'll just go ahead and write that in, 0, 0, 0. And then along the bottom, as it shows here, we all get 0, 0, 0, 0, 0. So now we just need that omega hat. Here is the formula for omega hat. Well, we know that omega equals 0, 0, 1. So omega hat 1 equals, we'll have zeros along the main diagonal. And then the third component of omega is 1. So here we'll have 1, negative 1. And then the first and second components are just 0. So we have 0, 0, 0, 0. So this means that our psi hat 1 vector is going to be 0, minus 1, 0, 1, 0, 0, 0, 0, 0. So there's lots of zeros here, which is going to be convenient for when we actually do the multiplication. Now for the prismatic joints, that's 2 and 3. Psi is just going to be that velocity vector, linear, angular. And then psi hat is going to be mostly zeros with the velocity vector. So to do psi 2, then we have V in the top, omega in the bottom. We know omega is just going to be 0, 0, 0. And then the V in the top will just be D2 dot, which goes in the vertical direction. So that is original Z. So we have 0, 0, D2 dot. Linear and then angular. So then squiggle 3 is going to look very similar, but instead this velocity points to the right, which is in the y direction. So here we'll have 0, D3 dot, 0, 0, 0, 0. So now to get psi hat for each of those, then it will have basically zeros. So let's say this is a 3 by 3 0. 0, 0, 0, 0. And then the velocity, which for 2 is just going to be 0, 0, D2 dot. And then squiggle hat 3 is also going to be 3 by 3 zeros. 0, 0, 0, 0 in the bottom, and then 0, D3 dot, 0. So now we have the twists. Then the final thing to do is multiply all of these together times the home configuration and get to the final transformation. So for the final answer, we'll have T 3, 0 of theta equals e to the squiggle hat 1, theta 1, times e to the squiggle hat 2 theta 2 times e to squiggle hat 3 theta 3 times t 3 0 of 0, where e to the squiggle hat theta is this. This is the product of exponentials formula, and e to the omega hat I theta I for this part comes from Rodriguez's formula. This is the matrix exponential. So if you plug values into all of these, then you can get the configuration of the robot at any joint angles. Here's a Matlab simulation to help visualize the robot. This is going to show each of its joints moving consecutively. Now, for the actual code procedure, we use the exact same procedure that we use for solving these problems by hand. So defining all the constants, the joint origins, zero configurations, velocities, then getting the twists, the exponential products, joint transformations, the links, and then finally plotting. So let's run it. So there's joint 3 pushing out, joint 2 pushing up, and then joint 1 rotating.